Okay, application final. Number one. They start off hopefully fairly nice. You're told a contractor comes out and charges $35. In addition, they charge $22.50 for every hour. So I'm going to make T in hours of work to figure out what their final. I'm going to use C for cost. So it really is just build the equation, the nice linear equation, given slope and your initial cost. You're given slope, you're given y-intercept, make a line. Then you see you're asked, that's the model, make sure you write your model, and then use it to say what happens after 6 hours of work. So the cost after 6 hours of work, I'm going to write this more like a line because I feel like it, plus 35, and figure out what your cost value is. Hopefully that problem isn't too horrible, but lines are one of the things you're responsible for, so we should be able to handle a line. The big thing is don't make a problem like this too complicated, and make sure you answer it in a sentence. I think it's something to the effect of 170. What does it do in my head? I don't want to do it in my head. No, 170. Okay, so it's a nice 170. So the contractor charges $175 to do that. Make sure you write it in a sentence. The contractor charges $170. Make it a nicer sentence than that. But lines, you should be able to handle lines nicely. The big thing is don't lose points on those. Make sure you're staying nice and focused. Okay, number two, the fence problems. Again, everybody loves fence problems. Okay, that might not be true, but fence problems are a good metaphor for restricted resources. In this problem, the one you have here is the classic river, and you're building three sides. A lot of people have done this often enough that they know the relationship. Be careful of doing it that way, because on tests, as you've seen, add in a couple more fences and you have to be able to figure out the new relationship. So make sure you're not just doing these by rote. But we've got three sides that we're building, and we have 350 feet of fencing. We've got two widths and one length we actually have to build. So what we're told we have to build is something such that 2W plus L has to equal 350. That's the relationship that we're given. What we're asked to do is find the length and width that will maximize area. And we know that area is equal to length times width. So we want to maximize length times width, given that this relationship for the 350 must stand. Well, if this relationship must stand, we could certainly say that that length is equal to 350 minus the two W's. So this is what L stands for, so I can put L in for L. So your area is going to be equal to 350 minus 2W times W. A little distribution will tell you that your area has to be 350W minus 2W squared. This is now a quadratic. Okay, its constant term is 0. Usually they have a constant term, but the W squared says this has to be a quadratic. The negative lead coefficient tells you that that quadratic is opening downward. That maximum value there is the maximum value that we're looking for. When the width is that value, you will get the maximum area. So we want to find the width that gives us our maximum. That's our vertex. And you remember your negative b over 2a relationship, or you could build the vertex form if you want to. So careful, a little bit careful though, the b is the 350, because of course that's the w to the first, this is the w squared. So negative 350 divided by 2 times negative 2 is 350 divided by 4. 350 divided by 4 is what, 175, 187. So 87.5 feet. And again, you might remember that relationship of it has to be a fourth when you have this exact structure. But again, if you add a couple fences in there, so you have to build, say, 5 widths and 1 length, or 7 widths and 2 lengths, you're going to change that relationship. So you have to know how to build this. So in this particular question, you'll ask what length and width of the plot will maximize the area. That's the width that maximizes the area. To find the length that maximizes the area, put that in for W. You'll find your length. In this problem, it'll be 175. So in this particular problem, it'll be 175 feet. And what will the maximum area be? You can either multiply those together, or you can put the 87 in for the W in your area function. And then just make sure you write yourself a nice sentence. The key, though, is building this relationship that you're told and putting that relationship into the area function. This is the relationship the problem is describing. You've got 2 widths and a length and 350 feet of fencing, and you want that to be interpreted in your relationship for area. So no matter what this happens to be, however many lengths, however many widths, that when solved is going in for your area. You've done a lot of these, practice these, you will see problems like this. They never go away. Number 3, you got a cave painting has 25% of its original carbon-14, of its original C14. Your instructor loves carbon dating questions, by the way. I do. And you're told that the half-life of carbon-14 is 5,715 years. Now, you've seen some problems like this. They're not going to go away either. They're very important, particularly for those of you going on to chemistry, sociology, some business applications, certainly chemistry and physics, certainly engineering, certainly mathematics, lots and lots of applications, some biology applications, half-life questions, and exponential modeling questions in general never go away. So the relationship that we know for, well, if we were trying to build a line, we'd be trying to build y equals mx plus b. This isn't a line, so we're not going to use that. This is an exponential model, because half-life tells you it's exponential. So you're going to use that amount at time t equals initial amount e to the kt relationship. This is really the exponential version of our linear models. This is our generic linear, that's our generic exponential. And in a similar way, because if we look at the y equals mx plus b, that m tells us our rate. Well, that k constant tells us our rate. That b is the y-intercept, it's our initial value. This a sub 0, a naught, is our initial value. Sorry. Now, if you're building a line, the first thing you would do is you'd look for a pair of points, build your slope, build your line, and then you'd use that line to answer your subsequent question. Same thing here. We want to use what we're told to figure out our model, and then use that model to answer the question. So we're told we will go from the total 100% of our carbon-14 after 0 years turns into 50% of our carbon-14 after 5,715 years. That's what it means to be a half-life. You go from all of it to none of it, or sorry, all of it to half of it in 5,715 years. So according to this model, we will have 50%, I'm just going to use 50 for 50%, of our carbon, that's our amount, given that we started with 100% of our carbon. If we decay exponentially, e to the k is our exponential, for time 5,715 years. Simplify this, or solve this actually, divide by the 100, reduce that to 1/2 is e to the k 5,715 years. Now a lot of people start half-life questions here. We go from 1 whole to 1/2 in 5,715 years. You want to start here? Start here. That's great. You want to use this as 1 and 0.5 and then divide the 1 and get the 1/2. Great. However you want to start it. Notice, by the way, we haven't used this 25 at all. That 25% is part of the question statement. We need our model first. Again, we're just like we're trying to build our line, we're trying to build our exponential model so we can use it to answer questions. To solve this, we're going to use our natural log. So the natural log of 1/2 equals the log base e and the exponent base e undo each other. So k times 5,715. Divide your 5,715, divide your 5,715, and you will find your value for k. Do be careful when you put this into your calculator. Your calculator will express it in scientific notation because it is like 0.0002 something, or 1, something. I don't remember exactly what it is. But be sure you're careful and you recognize that that is in scientific notation. This is a very small number. It's a very slow decay. Well, not for elementals, but anyway, that number will be given to you in scientific notation. Consider using the store function on your calculator to store it, just so you can use it more accurately. So this tells us that the model that we now have, our amount at time t, will be equal to our starting amount. It starts with 100% of its carbon. And this k we now know. We know that k, I'm going to put a little k star. That's the k that we found here. And our goal is to find the time that takes it to get to a certain value. So this is the model. We start at 100% of our carbon. It decays at the rate we found. This k is going to be that rate that we found. You put in a time, it's going to tell you how much carbon is left. You put in an amount of carbon, and you can figure out how much time it took. So now we were asked, how long does it take? Find the t, such that the amount will be 25%. And again, if you want to put this as a 1 and that is 0.25, you're welcome to. Heck, you could put that as a 1 and that as a 1/4 if you want to. Doesn't matter. So 25 has to equal 100 e to the k. Again, I'm putting the little k star because that's the k we know, times t, and our goal is to solve for this t. So divide by the 100, divide by the 100. You get 1/4 equals e to the k star t. Going to take the natural log of both of those. So the natural log of 1/4 equals k star t. We're trying to solve for the t because we already know the k. So divide by that k star. Those cancel. And our time equals the natural log of 1/4 divided by that k. Now if you have the actual k and you have the actual t, you can find out your actual values. So this constant, let me look it up, should be approximately equal to negative 0.000121229. Again, your calculator will often give it to you in scientific notation. Make sure you're careful about that. You can store this, you can keep it exact, you can do it however you'd like. So you take the natural log of 1/4, divide by this k value, and you'll find t is somewhere around 11,429.6 years. Again, make sure you answer that in a sentence. All of these application problems should be answered in sentences. So the cave paintings are 11,429.6 years old. Whenever you're doing an exponential modeling question, you always want to break it into these two steps. Use your given information, either a given population data, half-life, whatever you happen to be given, to determine what the constants in your model are. Once you've determined the constants in your model, use that model to answer the question. One of the big things that happens for exponential modeling questions to go wrong is people try to use all of the numbers all in one model all at once. This 25% of the carbon is happening at a different time than the half-life of the carbon. Now, this 25% and this 5,715 years are not related. They're not happening at the same time. They can't be part of the same model. So make sure you're doing them separately. Just like, given 2 points, you could make a line and then use that line to answer subsequent questions. You focus on the 2 points to build your line, then you plug in the problems or the numbers for your question. Building an exponential model follows the same logic, it just uses some bigger tools. Okay, so that's the first section. I can get one more in here, I think. So number 4 here, it's about birds. It's also an exponential modeling question. Don't worry about the sections. That's again for the 2-day final. You guys will take it all at once. Bird species is recovering from the brink of extinction. So 7 years ago, so we can call that 7. I'm just going to write 7 years ago. The population was 435. Today, so now, the population is 1240. How long will it take the population to recover? So how long will it take to get to 7500? Now, if this was a linear relationship, you would take these, once you figured out what numbers you wanted to use for the time, you would take these numbers and build your line. But you're told specifically in this problem that it's happening exponentially. So you want to make sure you handle it exponentially. That means you will be using the AT equals A naught e to the KT. That's our basic exponential model. But the logic is still the same. This is your question statement. I've boiled down your question statement. You'll use your given relationship to find your model. Then once you have that relationship, you'll ignore all that and then use this 7,500 to answer the question that's being asked. So the first thing we have to figure out is how we want to handle the time. Do we want to call 7 years ago -7? Do we want to call it 0 for the start? However you want to handle it. I think, let's see. Well, I'm going to call it 0 and 435. And then I'm going to call it 7 years for the 1240. So I'm calling time 0 this 7 years ago. So 7 years ago, I'm calling 0. So now is 7. And we want to know when it has grown all the way to the 7500. So what this means is that our initial value was 435. We grew exponentially, so e to the k, that's our grew exponentially. For how long? Well, this took 7 years, for 7 years. And after those 7 years, we had 1,240 birds. You want to try to make sure you can read this in that way. I started at 435 individuals. I grew exponentially for 7 years and ended up with 1,240 individuals. That's what this relationship is expressing. Our goal is to find the constant that tells us how fast that growth actually was, again, so we can answer subsequent questions. So I'm going to divide both sides by the 435, divide by the 435, get the 1240 divided by 435, whatever that is, equals e to the k times 7. Again, your natural log gets rid of your e, so the natural log of 1240 divided by 435, you can simplify that if you want, equals k times 7. So the natural log of 1240 divided by 435, all divided by 7, is going to be your k. And again, you can clean that up some, but really in practice, we're going to use that decimal approximation. Now, as I said, it's probably nice, if you haven't already, to look at how to use that storing function in your calculator. So you could store this value, but this value is somewhere around, let me look that up too, 0.1496, 0.1496, 458, something like that. Exponentials are very sensitive to little round-offs, so it's nice to keep as many decimals as you can. Again, if you store this constant in your calculator, you'll actually be storing 27 decimals, so it helps it be nice and accurate. But, at least keep 4, 5, 6, 7. You keep as many as you can comfortably work with. So that means our model is the amount that we will have at time t is going to be our starting amount. We've defined our starting amount as 435 e to the k. Go ahead and put my k here. I'm going to round it to 0.15, though I won't use that when I actually calculate t. So you put in a time t, and this will tell you how many birds you have. You ask how many birds you have, you can find a time t. So we're asked, how long does it take to get to the 7,500? So 7,500 equals 435 e to the, that's my rounded k, t. Again, notice your solving technique is very much the same as it was over here. Divide by the 435 equals e to the 0.15 t. Use your natural log to get rid of the e. Natural log of 7500 over 435. Excuse me. Again, you could simplify that sum first if you wanted to. Natural log and e undo each other. The log base e and the exponential base e undo each other. That's their job. So 0.15 t divide by 0.15 divide by 0.15. And we have our time is equal to the natural log of 7500 over 435 divided by, now this 0.15 I've kind of carried in this form for convenience, but again, it's good to use as many decimals as you can, even your stored value. Heck, use this whole thing if you want to. And I believe this is somewhere around 19 years-ish. And of course, you'd write a sentence, the birds will recover after 19 years. Be a little careful, that is 19 years from 7 years ago. So your sentence might be something like, it will take 12 more years. Because as soon as we define this as 0, we defined our time equals 0 as 7 years ago. So it will take 19 years from 7 years ago, so that's 12 more years. If you let this be 0 and that be -7, you'd have ended up with that 12 directly, but you'd have had to have dealt with the negative along the way. Again, either way is fine. It's just good to have your own preferences. Okay, let's end this one and start another one.